Hi guys, we're going to solve some harder differential equations today, and we're going to figure out the different methods for solving different types of equations. So let's have a look at the different sorts that we're going to look at. So you can see behind me, we've got separable differential equations that we've already looked at. So we're not going to go over them today, but they've got that form f of x times g of y. The other sort, or the method that we're going to use, is the homogeneous differential equations. And these are dy and dx equals some function of y over x. And lastly, we've got one that we're going to use an integrating factor to solve. And these are in this form that you can see here, where they're dy and dx plus some function times y equals some other function of x. And you'll notice that the y is just by itself, and that's quite important to see. All right, so in a minute, I'm going to show you some examples of these, and we'll go through the methods to solve them. Okay, so here are three examples of homogeneous differential equations. So you can see they don't quite look exactly like this form that we want them to be. So we want them to be a function of y over x. So let's see how we can just change them a little bit to get them in that form. Okay, in this first one, we do a little bit of a trick. So you can see we've got x plus 2y over x. What we're going to do is we're just going to split it up. So we're going to split this fraction into 1, so x over x, plus 2y over x. And hopefully you can see this is just 1 plus 2 lots of y over x. So now we've got it in that form that we wanted. It's now a function of y over x. We've got y over x's in here. In our second example, and I'll come back to this one in a minute, don't worry. In our second example, you can see we've already got a y over x, but here we've got an x over y. So let's just change this a little bit. Our first one we can write as y over x to the power negative 1 plus another y over x. So we can see it was really easy to change this into a function of y over x. All right, third example. Again, trickier. How can we possibly do this? And when you see fractions like this, you're probably thinking, oh, what sort of methods can I use? One of them might be to use difference of two squares, for instance. Okay, but in this case, not the right method. Our other method, do you remember we have used some methods where we divide top and bottom by the same thing? And that's what we're going to do here. We're going to divide top and bottom by x. And just have a think about for a moment what that's going to do. So, when we divide this top part by x, we get 1 minus y over x. When we divide the bottom by x, we get 1 plus y over x. And can you see, there we go, we've changed it into a function of y over x. Good stuff. Okay, so let's now go to trying to solve one of these. So I'll try and solve this top one. So let's go back. So we started with this function, we were able to turn it into a function of y over x. What do we do now? Okay, so what we're going to do is we're going to let some function v equal y over x. And if we do that, we can now rewrite this as y equals v times x. Okay? Now if y equals v times x, we can differentiate this, can't we? So dy and dx would equal, let's see, vx, that's a product rule, isn't it? So we've got to do v times the derivative of x, that's 1, isn't it? Plus x times the derivative of v, so dv by dx. Okay, so there we go, we've got an expression for dy and dx. But we already had an expression for dy and dx, didn't we? We have that it's 1 plus 2 y over x, which is 1 plus 2v. So this has to equal this. So we can say, therefore, 1 plus 2v equals v plus x dv on dx. Okay, so we've got somewhere, haven't we? But we've still got v's, we've still got x's. What are we going to do? Okay, we're going to use integration, as we have been with the other differential equations. But to do our integration, we've got to get everything with a v on one side and everything with an x on the other. So let's try that. So taking this to the other side, we get 1 plus v equals x lots of dv by dx. Now I'm going to do some maths here, which it's okay. It's not great. But I'm going to move the everything with a v to this side and everything with an x to the other. So we end up with 1 over x lots of dx equals 1 over 1 plus v dv. So everything with a v is moved over here, everything with an x is moved over here, and I just moved the dx and the dv. That's the bit that's not entirely mathematically rigorous. From here, we're going to integrate. So the integral of 1 over x dx equals the integral of 1 over 1 plus v dv, and we end up with ln x, or ln absolute value of x, and I'm just going to put a plus c here, equals ln of 1 plus v, or v plus 1, doesn't really matter which way around we write that. So remember, I could have written the plus c over here, I just choose to write it here. Okay, I'm running out of space, so I'm going to have to do some erasing. Okay, so we've got ln x plus c equals ln of 1 plus v. Let's give ourselves some room. We can bring this c in. Do you remember? If we let ln a equal c, we can bring this inside. So we get ln of ax equals ln of 1 plus v, where a equals ln c. Oops, sorry, c equals ln a. What am I saying? Okay, c equals ln a. Okay, so we can bring that a inside. And from there, we can solve this, can't we? So we can say, therefore, ax equals 1 plus v. Now, Alex asked me, why don't we have plus or minus here? Very good question. Okay, Alex's question, why don't we have a plus or a minus here? Well, we could, but do you remember when we write plus c on the end of our integration? We don't write plus or minus c, we're just dealing with c as a constant. Here, a is a constant, it could be positive, it could be negative, so we don't need to worry about that so much. So in this case, we get ax equals 1 plus v. We can now go from here and we can say ax equals 1 plus, well, v was y over x, wasn't it? And we're going to be able to now express this just with y as the subject. So that's not too hard. Let's multiply through by x, I guess. Ax squared equals x plus y. Y equals ax squared minus x. Okay, there we go. We've solved our homogeneous differential equation. Well done. Okay, so let's have a look at some examples of one that we solved with integrating factor. And you can see here our first example is written in the form that we want. So we've got dy dx plus some function of x times y equals some other function of x. So done for us. In our second example, it's pretty close, isn't it? We can see we've got dy dx minus something times y. So we've got dy and dx plus negative 1 over x times y equals some function of x. Okay, so pretty straightforward as well. And in the last example, again, doesn't take much to rearrange, doesn't it? Does it? We could take this to the other side. Dy and dx plus cot xy equals cos x. So we can see we get it in this same form where it's dy and dx plus some function of x times y equals some other function of x. Really straightforward, isn't it? Okay, so how do we go about solving it with this integrating factor? And what is the integrating factor? Well, the integrating factor is given to you on your formula booklets. You can see it up here. So it is written down there, e to the integral of p of x dx. So p of x is this term here, in the first case, the 3x squared. It's this term here, the negative 1 over x, or it would be cot x in our last example. So it's whatever is multiplying the y. And do you remember I said we can notice these because there's always just a y in them, okay? All right, let's go on and try and solve them in a sec. Okay, so try to solve this first one. If we want to solve it, we've got to firstly figure out this integrating factor. So let's do that. So the integrating factor in this first one is just e to the integral of p of x, which in our case is 3x squared. And this is really easy, isn't it? Integral of 3x squared is x cubed. Okay, and in these cases we never worry about the plus sign. Okay, so now that we've got that e to the x cubed, what do? We multiply everything in our equation by this. So it needs to be in this form. So let's see what happens. Okay, so all I've done is I've multiplied all of the terms by e to the x cubed. Now here's the critical bit, and I'm just going to turn you around a tiny bit. Okay, we're going to notice something here, and it comes down to our product rule. We're going to use our product rule in reverse. So let's have a look here. So if our u were e to the x cubed, and our v were y, can you see here that I've got a v dashed and I've got a u, and over here I've got e to the x cubed times 3x squared. That's u dashed, and I've got a v. Okay, so hopefully you can see here that I've got this product rule happening, and that is because of the integrating factor that I've chosen. Okay, that's why this method will always work. So by noticing this, we know that if we integrate this, if I integrate this, I'm going to get uv, aren't I? Because of the product rule in the reverse. So when I integrate this, I get uv, which is e to the x cubed y. And this is going to equal the integral of what's on the other side, of the 6x squared e to the x cubed dx. Okay? We happy with that? So I noticed that this with this, and so when I integrate it, I'm going to get this. Let's now look at integrating this side. It's not too hard, is it? Because hopefully you'll notice that e to the x cubed, when I differentiate it, I get this bit coming out too. I get 3x squared. I've got a 6x squared there. So I'm not going to go through the whole substitution process, but hopefully you can see that this would be 2e to the x cubed plus c. Okay? We're happy with that. 2e to the x cubed, if I differentiate that, hopefully you can see I'd get that. Yep. Okay, and now we've got something which isn't too hard to deal with, is it? Okay, so we've got something that we can rearrange and get y as the subject. So let's divide through by e to the x cubed. We get y equals 2 plus c e to the negative x cubed. So I divided this by e to the x cubed, I divided this by e to the x cubed, and I divided this by e to the x cubed. And there we go. We've solved our problem. So this integrating factor will always get it into this form, which is the product rule. And we can work backwards. We can integrate it to just make it the product. Okay? Are we happy? All right, well done.